Okay, we are now live. But I think we can wait 1 minute for our attendees to join us.
For me, it says the session starts in 3 minutes. I don't know if it depends on the clock on your computer, because you said it's only 1 minute left.
It's the same for
me. Maybe my computer is 2 minutes earlier. Oh my God.
For me, 2 minutes.
You're so eager to start.
Okay, the participants.
I think they can't join before the session is officially started.
Okay. So I started earlier.
Yeah, I don't think there's a join button until the exact time.
Yeah.
Mine is now 50 seconds, so my computer is 2 minutes earlier. Yeah.
I'll be right.
Okay. Hello, Nicole. Thank you so much. Yes, they all join. Okay, I think we can start. And hello, everyone. Welcome to our session. This is the session entitled Experimental Design. Thanks to our attendees and speakers in this event. Each talk will be in 15 minutes. And after talk, we have 5 minutes for questions and answers. You can type your questions in a Q&A box. I will ask at the end of each presentation. Our first speaker is Kristen Hunter. Welcome, Kristen. She has recently finished her PhD in statistics at Harvard and will be joining to the New South Wales University. Okay, Kristen, the stage is yours. Thank you so much.
Thank you. Thanks for joining today, especially to start off the session with a kind of unsexy topic of statistical power, but one that is very important. So I'll be introducing today the PUMP package, which stands for the Power Under Multiplicity Project. It's joint work between researchers at Harvard and MDRC. The slides are available on GitHub. I will also be posting the link in the chat at the end. So let's say I have an experiment with multiple outcomes. For example, I am running a dog competition, and I'm trying to test out a bunch of different outcomes for the dogs, evaluating their performance on jumping, on ramps, and on slalom. When I have multiple outcomes, I need to use a multiple testing procedure in order to obtain valid conclusions. The most standard one is a Bonferroni correction. That's when we just multiply all of our p-values by our number of outcomes. But there are many other potential multiple testing procedures as well. When I use a multiple testing procedure, that's going to change my power in my study, my power to detect true effects. The problem is that current practice for calculating power usually does not take into account the fact that people are going to be using MTPs. So that's the motivation behind the PUMP package. It calculates power when we have multiple outcomes. Multiple outcomes result in multiple hypothesis tests. And it specifically is for the setting where we have a multi-level randomized controlled trial. A multi-level experiment is one where we have a hierarchical structure such as when we have students nested within schools, nested within school districts. And I will be using education as a running example throughout the talk, although we do see multi-level experiments in other settings, such as or people in congressional districts. You can see multi-level trials in a variety of settings. And I will be assuming that the analysis that people are using are going to be frequentist mixed effects models. If someone wanted to use, for example, a Bayesian model, then the whole power calculations would be different. So just for the setting of this power calculation, we will just be assuming regression models. So let's consider an example of a study where I have multiple outcomes. Let's say I have 3 outcomes and I have a 2-level block design. So that means I have 2 different levels of hierarchy, for example, students in schools. And a block design means that I randomize students blocked within each school. So half of the students in each school is assigned to treatment and half is assigned to control, for example. If I calculate my statistical power to detect the effect for any of my 3 individual outcomes, if I don't do any adjustment, my power is around 80%, which is what we usually target in a randomized. However, if I use a Bonferroni adjustment, which is what I'm supposed to use, some sort of MTP, my power drops to only 67%. So at first I might be a little bit sad because by adding these additional outcomes, I've actually reduced my power. Basically, I started off with I thought was the dog on the left, but it turns out what I had was the dog on the right. Although the story is actually a little bit more complicated than that, I will talk a little bit later about how we can actually sort of expand our definition of power in order to actually not lose power in the setting with multiple hypotheses. There are a lot of different factors that affect power. I'm going to go through this relatively quickly because this could be a whole talk all by itself. If we have a single outcome or more, we need to think about the design of the study, basically how many levels we have. We need to think about the regression model we're going to use. We need to think about the sample size, so how many units are at each level, the proportion of units that are treated. We need to make assumptions about our covariates, how many covariates we have, what is the R-squared explanatory power of them, and also the intra-class correlation. This is just a term that describes how variation breaks down between different levels. So of all my variation, is it mostly in the student level, in the school district level, et cetera. And then once I have multiple outcomes, I have a whole bunch of new considerations. So I need to consider what definition of power I'm interested in. I also need to think about how many outcomes, which means how many tests I'm going to run. There's a big difference between having 3 outcomes and 100. I need to consider the correlation between my test statistics. So for every outcome, I'm going to run a hypothesis test. That hypothesis test will involve a test statistic, and all of these test statistics will have some correlation structure, and that will affect my power. I also want to think about how many of my outcomes I think are truly significant. So if I have 100 outcomes and I think only 10 of them are real, and maybe versus that's going to be very different than if I assume that all of them have significant effects. And finally, the multiple testing procedure I use, depending on which one I choose, will also affect my power. The first step in calculating power is I need to figure out my setup. So first, I figure out the design of my experiment. How many levels am I going to have? We support up to 3 levels. You could have more, but it's somewhat rare to have 5-level experiments. And then also at what level randomize? Are you going to randomize students or schools or districts? And these correspond to things like block designs, cluster designs, block cluster designs. And we support randomization at any level. Second, I'm going to think about how I want to model the experiment. So what regression model do I want to use? As I mentioned earlier, we're assuming mixed effects regression models, which means that at every level, I assume that intercepts are either fixed or random. And my treatment effects, so for example, let's say I'm thinking about treatment effects for schools, I might assume that all of the schools have the same treatment impact. I might think that they all have different treatment impacts, but they're all fixed. Or I might think that they have random effects, which means that they're all drawn from some shared distribution. This is obviously a lot of different choices, so we do have some notation behind it that I'm not going to go through today that kind of defines what all of these different choices that you make. And on the right side, I've just listed all of the different designs and models that are supported in the package. Again, I'm not going to go through what they all mean, but just to give you a sense of, that we support a wide variety of choices. Something I've previously mentioned is that once I have multiple outcomes, I can actually expand my definition of power from what we usually think about. So individual power is what you probably have learned in your, like, if you've taken statistics classes. Individual power is the probability that I reject a particular null hypothesis. When I have multiple hypotheses, I can expand this to think about what's the probability that I reject at least one. So if I have 5 outcomes, maybe I only care about whether I have just at least one of them being significant. I can also generalize this to d minimal power. So how much power do I have for half of them to be detected, or 2/3 of them to be detected? And finally, complete power is the strictest. It's the probability that I reject all of my nulls, that I say all of my outcomes are significant. Now, at first, it might seem like by expanding the definition of power, maybe I'm kind of cheating a little bit, but really it's just sort of redefining success depending on the context. So if I have a competition for the type of dog on the left, I'm going to have a lower bar than for a competition for the type of dog on the right. And that's not cheating, it's just redefining success based on the context. So for example, we might have different definitions of power if we are considering a pilot study versus some huge experiment that's run across multiple states. I might be more or less what my context is. And the final choice I need to make is my multiple testing procedure. This again could also be a whole talk all by itself, so I'm just going to go through these relatively quickly. The ones that we support in the pump package, the Bonferroni one is very simple, very well known, but it's also quite conservative, so it lowers your power a lot. Home is a slightly less conservative version of Bonferroni. The Benjamini-Hochberg procedure is kind of a different philosophical approach. It has a much less strict criteria, so it's less conservative, but and for some people it's actually too little conservative. And finally, the Westphal-Young procedures, there's 2 versions of them. They are permutation-based approaches. Because of that, they're very computationally intensive, but they do have very nice properties. They tend to not be overly conservative. So let's actually use the package. So after we load in the pump package, we can calculate power. So first I choose my design and my model. Then I choose my multiple testing procedure. Here I've chosen the Bonferroni correction. Next, I need to determine my assumed effect size. So how big of an effect do I think I will see in my outcomes? I tell it the number of outcomes I'm interested in, and then I tell it sort of the structure of all these parameters that I mentioned before, the sample sizes at various levels, my proportion of treated units, my significance level, how many covariates I are squared, my intra-class correlation, and my test statistic correlation. And again, I apologize for going through this, but there's so many parameters that I don't really have time to go through this in detail. And this is the output we get. So we get a table of power across a bunch of different definitions. It shows what would happen if we didn't do any adjustment, which not, we're not saying that this is a good thing, but just for comparison, if you just ignored the fact that you were doing multiple testing and just did no adjustment at all, we get an individual power of around 80%. And these individual powers are for each of the 3 outcomes, and then the mean across the 3 outcomes. And then we can compare that to if I did a Bonferroni correction, I can look at my individual power. And with the Bonferroni correction, I now can look at my other definitions of power. So this is 1 minimal power, the probability that I detect at least one of my outcomes, 2 minimal power, and complete power. And if we look at this table, this is just a sort of a generalization of the example I gave before, where now that I'm considering 3 outcomes instead of just 1, I have lost individual power, but I've gained 1 minimal power. So my 1 minimal power is higher than my uncorrected individual power. So if I'm less strict about my definition of power, I've actually gained something. And the last thing I'll note is that complete power is always going to be the lowest because it is the strictest. It's the probability that we detect results on all 3 of our outcomes, which is a strict criterion. I briefly want to talk about how the package works. So if you've done power calculations before, maybe in a stats class, often there's a formula. You just sort of like plug and chug and you get some answer out. And unfortunately, we can't do that here, in part just because there is such a wide range of things that we're considering. So we have different designs, different models, different number of outcomes, different MTPs, different definitions of power. So we would have to calculate a formula for every single one of those settings, including for every single possibility for number of outcomes that you want to consider. And that quickly becomes infeasible. And in fact, in some places, actually impossible. So the Westphal-Young procedure, because it's a permutation-based approach, there's no like nice algebraic answer for power. You actually have to calculate it by hand. So instead of that, we use a simulation approach. So you can imagine calculating power through simulation is first you simulate data according to your alternative hypothesis. So you simulate an experiment where all of your outcomes are significant, for example. Then you calculate test statistics and p-values like you would normally, like maybe I just run a linear regression and outcomes. And then I calculate power using all of the p-values that I've calculated. So if I've run 100 simulations, I see how many of those simulations did I have a p-value less than 0.05, and that is my power. I get an estimate for power. And I'll note that it's an estimate because of the simulation-based approach. It's not a precise number. This works to simulate data like a bunch of times. So we can actually, in this setting, we can simplify this a little bit by skipping a first step. And that's because given a certain design and model and a known correlation between test statistics, we actually know the distribution of the test statistics. So basically, we know that we're going to have some variant t distribution, and we can treat them accordingly. And that means that we can skip the whole simulation data step, and we get much simpler and faster power calculations. So we just jump straight ahead to sampling test statistics, and from there we calculate p-values and power. There are two other main functions in the pump package. One of them is calculating the minimum detectable effect size. So often we don't really care about power in itself. We often care about power as a means to an end. One of those goals is often the minimum detectable effect size. So basically, let's say I have a power of 80%. What is the smallest effect that I could detect? Of 1, is it different than 2 groups of 0.1? So we can sort of backward calculate that from the power. Or we might want to be interested in sample size. So let's say I'm designing a study prospectively, and I think I have an effect, I think I'm going to see an effect size of something, and I know I want to target power at 80%. How big of a sample size do I need? How many students, schools, districts do I need? And both of these approaches are a little bit more complicated than power because we have to use a search algorithm to search over a bunch of different powers and then to see what corresponds to the correct value of MDES or sample size. Just to show you an example of sample size, here is a calculation of sample size. We plug in our target power, our power definition, and the type of sample size we want to calculate. And it tells us, hey, if you want one minimal power of 80%, you need a sample size of 7. And I have one more feature that I want to emphasize, which is there's also a grid function. What it does is that it allows you to assess the sensitivity of your power to all these different parameters. So all of these parameters that I have to plug in, some of them I know, such as sample sizes, but some of them I kind of have to guess based on prior knowledge, such as the R-squared values or my correlation between test statistics. And so I might want to assess how much these assumptions are actually influencing my power. So what we can do is we can plug in a sequence of values and then compare power over that sequence. So here I'm varying my correlation between test statistics, and I'm also going to compare a bunch of different MTPs. So here I have on the x-axis, I have my rho as it changes from 0 to 1 and my power. And I can look at it across a bunch of different definitions of power and across a bunch of different MTPs and see, you know, if I guess that my rho is 0.4 and actually it was 0.6, like how far off would I be? So to summarize, PUMP is an R package that estimates power for multiple outcomes for multi-level RCTs. It takes into account the use of multiple testing procedures. It calculates minimum detectable effect size and sample size. And one of the, a very important, that last feature that I highlighted, the ability to assess sensitivity of power to different parameters, is also really useful. Even if you're running a study that's not a multi-level experiment or you don't have multiple outcomes, a lot of existing power software doesn't allow you to easily explore. So even if you're, you know, don't need all the extra complex stuff, PUMB is also really helpful for that. I want to thank the Institute of Education Sciences grant for this work. And finally, here are a bunch of links. The package is available on CRAN. We have a Shiny app. The code is available on GitHub. And we also have a paper on arXiv. And if you have any questions or comments or feature requests, please get in touch with me. Thank you.
Thank you so much. I like your last slide. It was great. Thank you so much. We have two questions. Let me ask them. Does this method allow for different sample sizes in each group or blocks? Our first question.
So currently, sample size across the blocks. So if one school has 100 students and the other one has 300 students, you plug in 200 students, and it ends up usually not affecting power calculations too much to the average. I'd have to think about whether if you have like really vastly different sample sizes, we don't currently accommodate that, but I don't think it would influence your power too much. Good question.
Thank you so much. And the next, does the definition of good change for the different definitions of power? For example, for this power, consider greater than 80% to be good. For that, consider greater than 75% to be good, etc.
That's a really good question. I don't 100% know the answer to that because these like expanded definitions of power aren't used in practice as much right now. I think that there aren't as strong conventions. 80% is, as you say, it's good, but like it's just a rule of thumb that we've come up with, right? And so I don't know if people have come up with rules of thumb for the other types, or if it's still sort of good practice to keep 80% for all of them. I'm not actually sure. Thank you.
Okay, thank you so much. And we don't have any questions, so we are going to our second speaker. It's Carlos de la Calle Arroyo. He has a background on mathematics and computer science. He has got a PhD on statistics by the University of Castilla-La Mancha, in which he works as an adjunct professor. His main research is on optimal design of experiments. And thank you so much. We are waiting for you. The stage is yours.
Thank you. Hi, so I'm Carlos de la Calle Arroyo, as she said, from University of Castilla-La Mancha, and I'm going to present the OptethR and optimal experimental design package. First of all, a small outline of the presentation. We're going to see the features or the different functions or functionalities of the package, which are optimal design calculation, evaluation of design and the OptES class, design augmentation for the optimality, and efficient rounding of exact approximate design, the shiny demos of the package, and finally a brief summary and future improvements to the package. First of all, about optimal design calculation, I'm gonna go through a brief introduction of optimal experimental design in order mostly to establish the notation. First, we consider a regression model on a single variable x, where an error of the exponential distribution family, where theta is the unknown parameters of the model of interest for the experimenter. The notion of an exact design is known, a collection of points with replicates in which we take measures. An approximate design is seen as design as a probability measure. We are going to consider discrete with probability measure with finite support over the design space, where the weights are the proportion of observations to take at each point, which has nice theoretical and practical properties. We're going to define the usual feature information matrix, and for that we have several optimality criteria. In this case, we are going to consider optimality criteria that depends on the information matrix, namely some of the most used in literature, which are the optimality, which minimizes the confidence ellipsoid of the estimators of the parameters, the optimality, which is the same for a certain subset of S parameters, A optimality, that minimizes the average of the variance of the estimators, and I optimality, which minimizes the the variance of the prediction over the region, over the interest region R. And as I said, approximate design allows us to have this nice result, which is the general equivalence theorem, which not only allows for to verify or check optimality of a design, but also give us tools for algorithms that allow us to calculate these designs. And we define the efficiency of our designs as the quotient of the corresponding criteria functions. So in this package, we have implemented a version of the Cocktail algorithm proposed by you, in which we combine both an iteration of the very well-known Wien-Fedorov algorithm, in which we have at each step the point that maximizes this expression here. That comes from the general equivalence theorem. And then after adding each point, we optimize the weights via a multiplicative algorithm. And then we applied a couple of heuristics in order to both join points that are very close to one another and delete points that have very little weight within the design. This multiplicative algorithm proposed by Thorsney starts on a non-singular design and updates the weights recurrently, sequentially, until a certain small difference between the weights between iterations is reached. With this algorithm, we have implemented the MDES function that allows us to calculate optimal designs for the criteria that we have seen before. We have to specify the optimality criteria, in this case, the optimality, the model, linear, or in this case, non-linear with respect to the parameters, as an R formula, the unknown parameters, the theta vector, let's say, the best guesses or initial values, which are only needed in case the model is non-linear, in which we calculate locally optimal designs, and the design space. Then we run the algorithm, which stops whether either at a check on the sensitivity function or a certain number of iterations. We give a certain bound for efficiency, which is the Atwood bound. And we give an MDES class object, which has the optimal design, supporting, in this case, for the Arrhenius model on 2 points with equal weights, the sensitivity function, the attribute of the model, in which we can check graphically the optimality, the convergence of the algorithm, that is how the criterion function has changed over the number of iterations, and the criterion variant for the function, in this case the square root of the determinant. We can also calculate for other optimality criteria, namely which we just changed here to A optimality, DS optimality, or I optimality. Some of them, as DS optimality and I optimality, are required to give either an interest region or a subset of parameters as a vector of index. And we can also, as I mentioned, calculate designs for not only for normally distributed homoscedastic model, but we can also define our own variance from the exponential family, in this case, a Poisson. And we give this as a weight function. In this case, we give the weight function, we have to give the square root of the elemental information matrix. And we can calculate as well optimal designs for the structures of the variance of the model. As I mentioned, the algorithm uses a couple heuristics, one that joins points that are very close together, and another one that deletes points with little weight. But these close together and little weights, in the end, are some notions that are dependent on the problem, and sometimes the predefined value that we have tried to tune so that they work fine for a decent array of modern problems. Sometimes they don't work as well as as it is this case, where we cannot find the optimal design. So the user, if he's a bit knowledgeable about the problem, can modify these parameters, some optimal parameters on the algorithm. In this case, we lower the join threshold in order to allow these points to be different from one another, and we can now reach the optimal design. Secondly, in order to evaluate design, since optimal designs are usually used as benchmarks, since they have little points, and are not really experimenters sometimes are not really keen on implementing extreme and very few points design. So we just use the design efficiency function to compare a given design as a data frame with points and weights with a certain object, an optimal design calculated by the algorithm, and we can give the efficiency of the user's design in order to check or use as benchmark. Just to mention, this design efficiency takes the criterion function from the design, so it always calculates the efficiency with respect of the optimality criterion of the object. And also we have implemented the print method, which prints the design. The summary prints namely all the information, the model, the weight, aka the distribution, optimal design, minimum efficiency, and criterion value. And when we plot the design, we have both the information matrix and the sensitivity function, and the support point of the designs with the weight or proportions of points beside each point. Regarding the augmentation, this is a bit of a work in progress. We have papers under review right now about it, and we're working on improving this, as I said. But what we have currently working within the package is the augment design function that allows to augment design with respect to the optimality. The arguments are similar to the opdes function, but namely we have to give a design to augment, either optimal or not, the weight for the new points, and then we are given a choice with the model parameters, etc. And then with a certain calculation, we are given a choice of feasible efficiencies of the resulting design, in this case between 70% and 95% approximately. We have chosen for this example 80%, so the function gives us a graphic tool in order to visualize what we call the region of candidate points, from which we can add any number of points with added weight 0.3, and the resulting efficiency will be higher than the 80% we have chosen. A simple example, just adding 360 and 380 with weight 0.5 will result in the augmented design with over 80% efficiency. And we can also augment non-optimal designs, in which case, since the efficiency we choose is relative to the initial design, with this procedure, sometimes we can even improve designs. In this toy example, let's say where the Michaelis Mental model, we are going to add 40% new observations on different support points than those of the initial design. We chose an efficiency of 1.3, aka 130%, and the final design ends up being more efficient than the base one. Just as a side note, the weights are always standardized by the chosen weight, in this case 0.4, so we always end up with a weight of 1 on the design. Regarding rounding, some of the criticism of approximate design is that it's not a feasible design to implement sometimes, depending on whether the weights are proportional to the number of observations we want to take. So Puckelsheim and Reader developed an algorithm to approximate design, to round design to an exact design, and we have based on their algorithm, we have automated it, so we can start with an approximate design with weight xi. We multiply this factor depending on the number of parameters and the number of points we want for our design, multiply it by the weights, round to the closest integer, and then if we have the number of desired points, then we are done, and we return this exact design with this number of observations, and otherwise we increase or decrease as needed the closest point to the nearest integer. As per how to use it, we can simply use we need to give a design as a data frame. For example, this here, and we can round the design to a certain number of points. In this case, 21, we have this rounding, and in case the sum is not exact, the function gives a warning, or gives the information that a proposed size of exact size is given here, and otherwise an alternative size with the desired n number of points is always the return of the function. We can check that the efficiency of the rounded design and see that effectively this algorithm of them is pretty efficient in translating approximate design to exact designs. And lastly, just to mention, we have a couple of demos that do not have the full functionality of the package, but demonstrates the functionality of both the optimal design calculation and the augmentation for a certain families of model. Lastly, just as a summary on future lines of development, we aimed at this making this package easy to use for experimenters and mainly use on real applications. Try to allow to calculate and augment design for a wide family of models and distributions, and allow us to run the designs in order to be directly used by experimenters. And we are aiming to, in the future, probably not that easy, but we'll work on it, on improve this by allowing models with several explanatory variables and augment designs for different criteria, which is a work in progress from the theoretical point of view. Here are here's the package slides and the reference of the package in CRAN. Lastly, thanks for your attention.
Thank you so much. It was great. I wonder if there is any question. If you have any question, you can ask in the question box. I will ask from our speaker. So for now, because we don't have any question, I want to go for our last speaker, Francesca Graziano.
There is one question, I think.
There is a question, I think, yeah.
I can't see it.
Is the design space?
The design space of the design space vector lists the min and max allowed in the x variable, not the explanatory variable, the values that we can choose to observe on the explanatory variable.
Okay. Because I can't see, sorry for if I didn't ask. Okay, our last speaker, she is a postdoc researcher from Italy at the University of Milan. She is a biostatistician and currently working on the use of epidemiological data. She will talk about package which she developed. Thank you so much. The stage is
Yeah.
yours.
Thank you. Thank you for the introduction. I share my screen. Mhm. Okay. So, sorry about that. Okay. So. Okay, something go wrong. Okay, so now, okay, so did you see my slide? Yeah?
Yes, perfect.
Okay, so thank you for the introduction. I'm working in the context of epidemiological studies, and usually the large longitudinal cohort and clinical trials often store biological specimens collected at the time of the recruitment. So we have a lot of data at the beginning, and could be used. These materials, this data, could be used to answer new research questions. But a lot of the time, it's very expensive to measure the biomarker for whole subjects in the full cohort. So we use an approach called phase approach that we can subsampling a group of subjects from the phase 1, so from the full cohort, in the phase 2. So we have a lot of materials and a lot of data from the phase 1. So we have the outcome and the coverage in the phase 1, and the biomarker is measures only for the phase 2. The advantages of this approach are a lot, because we use a parsimonious use of the biological specimens.
Sorry for interruption.
Sorry?
Sorry for
Yeah?
interruption. Can you please share the slides in presenter mode, because we see your presentation.
Present.
Perfect. Yes. Thank you so much.
Mm-hmm. I can try. So did you see?
Yes, we are now on just in the PowerPoint. We see your PowerPoint software.
Okay.
Please share
Yes. Maybe I share.
presentation mode, if it's possible.
Mm-hmm. Maybe in this way.
Okay, when you change the slides, we can't see the new slide.
Because so did you see this in this way? It's okay.
Siete pregati di portare fuori le macchine al parcheggio meno 2, grazie.
Oops, sorry. Did you see in this way?
Yes, okay.
Okay, so okay, I need to do zoom, or did you see? Do you see the slide? Okay.
We can see, but if you put in the presentation mode, maybe you can. Do you have two computers, two monitors, or just one?
No, because I changed the room.
Okay, we lost the screen.
So,
please share it again. Okay. Yes.
Maybe, okay, so share, I try again.
Yes, thank you so much.
Okay, sorry about that.
No worries.
I try. Did you see the slide?
Yes, we can see it.
Okay, it's okay now?
Okay, please start.
Okay. Okay, so the two-phase approach have a lot of advantages. So we have a clear picture of phase 2 derived from phase 1. We have a flexible use of the information from the full court and the opportunity to study different outcomes. But what is the critical part of the process? The critical part are which variable could be used from phase 1 and how can we estimate the power? So the motivation context comes from a study from children with acute lymphoblastic leukemia. We have 400 patients, and we want to measure a new biomarker, explore a new biomarker in a maximum of 120 patients. So we have a budget limitation, and we need to measure this type of biomarker because it's very expensive for a maximum of 120 patients. So the questions are, what's the optimal sampling design uses the information from phase 1, and can we predict the power in a decreased samples? So we developed with my supervisor a package called Design to Phase. This package performs a power estimation via simulation for two-phase sampling design, and there are a lot of steps that I show in this picture. So first, we generate the full court of dimension n using the information of phase 1. Then we conduct a different sampling process of phase 2, and we measure the effect of the biomarker on the outcome. And then the last step was to evaluate the performance for each sampling design. So we repeat beta simulations, and we have the power and design effect of this context. So first of all, we generate the phase 1 from target population. We generate a data set from baseline coverage. And now our package are developed
Sorry for interrupting, dear.
Sorry.
Your slides are just frozen for us. If you,
I don't know why. Maybe in this way.
In the presenter mode, at the bottom,
in the present.
you can change at the bottom of the PowerPoint. You can change the presenter mode, so we can just see the page, not whole PowerPoint, if it's possible.
Okay. Maybe. Okay. Sorry.
No worries, because the slides are just frozen for us.
I know. Yeah.
No worries, we have time.
So maybe I try in another way.
By the way, dear Carlos, if you want to share your slides and the links, okay, it's now okay.
Okay.
We see the PDF.
Yeah, maybe the better way. So what time? Okay, so we simulate a data set from baseline coverage. So we have an hypothetical risk factor and auxiliary variables that is a proxy of the biomarker, and we simulate the biomarker. Then the outcome was in time to event outcome. So we simulate also survival data from viable hazard model with scale and shape parameter, conditional on coverage, where beta 1 and beta 2 are the expected coefficient from the risk factor and the biomarker on the time to event outcome. We also simulate a censoring time from the exponential distribution, and the administrative censoring was set at the end of the follow-up. So this is now we have the phase 1, so that we have a simulated full court, and now we perform a sampling process. We explore different sampling design. We explore the simplest one, so the simple random sampling, the case control, the probability proportional to sites, and other two to design, because we are in the context of survival data. So we simulate also a sampling process called nested case control and countermatching. So here you can see on the left the classical one, the common one, so the case control stratified by the event and an hypothetical strata. And on the right we have a probability proportional to sites sampling design. In the other slide, there is another two sampling design. So we have nested case control and the countermatching sampling. The nested here we have the line is the follow-up time, and the solid line is the sampled case and control. So the control are sampled by the set of subjects at risk and event-free at the time of the event of the case. So if we have this case, we choose a control that is an event-free. On the right, we have a particular nested case control called the countermatching sampling. It's a particular because we select the control at the time of the case, but in the opposite stratum of the cases. And in literature, we see that this is one of the most performed sampling design, because we use discordant pairs of information. Then we use a subsample to estimate the effect of the biomarker on outcome. Due to the two-phase approach, we use a weighted Cox model for two-phase design, and the weight depends on the type of sampling design. So we use the inclusion probability for the sampling design, and we use the inverse of the inclusion probability. The power and design effect are calculated over the B simulation. So with the power is estimated as the proportion of phase 2, for which the null hypothesis of no effect of the biomarker of the event is rejected. And the design effect is calculated as the ratio between the estimated variance of the biomarker effect on each sampling design divided by the simple random sampling, the variance of the simple random sampling. The function is quite simple. The package is on GitHub, and we need to specify different type of parameters. So we have the first 4 parameters. We define the biomarker, the expected effect of the biomarker on the outcome and its prevalence. And if we have a risk factor, we need to specify the prevalence and the beta coefficients. We also add recently another option. We can use an auxiliary variables, so we need to specify the sensitivity and the specificity. By default, the function perform case control and simple random sampling, but we can add extra designs. So the next case control, probability proportion to size, and countermatching are the extra designs. And then the last parameters are to simulate the survival data. So this is the input, but the output are very simple. So the output are the expected number of the event, the type of design that we required, the explored sample size of phase 2, and the power and the design effect for each sample design. But now we show a little bit the results and in one application. So we I described before our motivation context. So we have 400 patients, and we know that the biomarker has a prevalence of 25%, and the expected effect of our biomarker is the hazard ratio of 2.5. We have also a risk factor, and we know the effect of the risk factor on the outcome. So we have a high effect of the risk factor on the outcome. So approximately 3 of hazard ratio. And using this information, we can plan a subsample of 100, at maximum 120 patients. So we run the code, and we briefly set an exploration of 80 or 100 or 120 subjects for the two-phase sample. And this is the output, but if we explore a different sample design, we can also use another function called plot power that we plot the power curves. So here there is a little bit some results. So we have each line correspond to the sampling design, and we have the most performed sampling design increase the sample size are the case control, the classical case control, but also the nested case control. So we have this type of information. So using a third of the full cohort, the power reached to 60%. And despite the risk factor that was very associated with our outcome, in terms of power, it wasn't a good choice in this context. So it's, in my opinion, is a good instrument to explore before running a two-phase study. So there is another example, but it's very similar. I have time.
We have just 3 minutes left.
Okay, so in conclusion, the sample size could be planned considering not only the budget constraint, but also the statistical power. And it's very important to compare results on efficiency, considering also various sampling design and varying different strata. Design to phase allow to stratification and explore different beta coefficients, and the library is easy to use also for not R user. This is the first version. So the next step could be more flexible function, different nature of coverage, because now it's only for binary coverage. Possible to consider 2 or 3 strata during the certification process. And we consider only the unbalanced design, so case control ratio 1:1, so we can improve also this type of sampling. And finally, the high dimensional data. I have also a thank you slide, so maybe, yeah, some references here, and thank you for your attention.
Thank you so much. It was great. So,
sorry for the problem.
No worries. If there is any question, please ask, because I have 1 minute left, because my computer is just 2 minutes before, ahead. So if there is any question, please ask. I can't see any question. So thank you so much again for our speakers. It was a really great event. And I myself really enjoy all of your talks. So if there is anything, if not, we can say goodbye to all of you, for our attendees and our speakers. Have a very good day or night, whenever you are. Bye-bye. Thank you so much.
Thank you.
Bye.
Thank you, Leslie.
No worries.